So thank you guys for your patience. This is a re-recording of a presentation I gave a few weeks ago at the LayerOne conference on photogrammetry, or how to make 3D scans with only a camera. So my name is Chris, also known as Machinist. I'm from 23B Shop, a fellow hackerspace out in Fullerton, just past the orange curtain. If you're ever down that way, do drop in. We've got a lot of cool stuff to play with, and one thing I've been playing with lately is a lot of 3D scanning and 3D modeling technologies, and naturally all of that path led me towards photogrammetry, which is a really interesting way to acquire a 3D object and to be able to render it in the computer, and not only render it, but in full color and rather dimensionally accurate. There is a bit of a process, and there's a bit of domain knowledge required to get to that point, and we're going to try and cover as many of those bases here in about the next 90 minutes. So follow along, jump in if you have any questions, because I'm here to explain things for you guys. And I got a fresh data set with this robot right here, and we're going to process all of this live, so hopefully I don't fall on my face. So photogrammetry, right? Who am I? Nobody really cares, except this is a 3D scan and 3D print I made of myself. So Yahoo. So what are we talking about when we're talking about 3D scanning? This is a really interesting crossroads in technology. There's a lot of science and math involved with what's going on. We're dealing with optical properties, dealing with like physical, mechanical engineering concepts. A lot of artistry is involved in this as well, because there's sort of an unspoken like guideline set that is required to achieve the best results using photogrammetry, and those are the kinds of things we're going to talk about today. So there's a dozen, 24 different styles of photogrammetry software we can use, and to take a step back here for a moment, this is not a new technology. Photogrammetry has been a technology as long as photographs have been a technology. The way that this has become so available recently is that computing power has become powerful enough and available enough that just about anyone off the street can, do this on their iPhone or using, cloud-based technology. And the software is becoming cheaper and freer to use. It's much, much more accessible now than it was 5 years ago. And there's myriad applications for it. If you're doing engineering, you can take a model of your part and import it into the computer. If you're doing if you're doing archaeology and you're trying to get a record of, some reliquary site out in the middle of, the Aztec Yucatan or something like that, you can take a bunch of pictures of whatever you're trying to scan and then reconstruct it in your computer later on. This is also good for, cultural preservation. You can use photogrammetry with drones to take, large-scale scans of very large areas or valleys, and, do like geological surveys that way. We can go on and on and on with the applications this is useful for, and that's pretty much why we're here. I want to show you guys how to use these amazing tools, and it's up to you what to use them for. So the software we're using here is a combination of a couple of things. We're using primarily VisualSFM and Meshlab. Those two programs work hand in hand to first acquire a point cloud, a three-dimensional point cloud, and then we have to use Meshlab to reconstruct that point cloud in a more coherent way for the computer to understand. VisualSFM it's freemium software. It's free to use for non-commercial purposes. The GUI is not open source, but the tools are open source. There is one technicality with that. All of photogrammetry relies on feature recognition technology, and the feature recognition engine in the VisualSFM package is called SIFT. And there is a patent on that in Canada. This guy, David Lowe, who developed the algorithm, just for full disclosure about that. There's a couple other little included packages which are all open source and available online, MVS, CMVS, to do the multi-view stereo, to like place the images in proper orientation in three-dimensional space. we've mentioned Meshlab, and I'm a huge fan of Meshlab. Anytime you have to deal with like 3D print files or any kind of it's a very powerful mathematical tool for dealing with 3D print files. If there's any small errors, if you need to, patch holes or something, Meshlab is pretty much the only game on the block. That's a result of some scholastic research at some universities in Italy that are primarily using that tool for cultural preservation. They'll take a bunch of pictures of famous sculptures from the last, 2 millennia, and, we can preserve them forever digitally just by applying this technique. So I'll shut the hell up. We'll see how this actually works in real life. So I've been tempting the demo gods, as I've been saying, and we'll see how this goes. So I've got my VisualSFM window open here, and another note that I'm thinking about real quick is VisualSFM is available on Windows and Linux and Mac. It is not easy to set up on Linux or Mac, so if that's your strong point, have fun. I'm a Windows guy, that's why I have it running on Windows. But one other interesting application I found recently is somebody has set up a Docker container with a photogrammetry toolbox already in it, meant to work on Amazon AWS GPU clusters. So if that's your bag, if doing like scalable computing is your thing, like that kind of tool set is available online for free. So if you want to do some powerful photogrammetry using other people's computers, that's an option. So I took a bunch of pictures of the robot here on the table, and we'll go ahead and open that up in VisualSFM. First thing we need to do is import the picture set and do some feature recognition. So let's see, it's in null right here. I took about 30 pictures of this robot here, and how many images you run through the software, it directly affects how much time it takes to process the software. It's about a picture a minute, but there's like an inverse relationship to that, obviously, and that's why I suggest using some AWS servers with scalable architecture is an interesting thought, because if you can apply one GPU cluster per picture, you get the results instantaneously. You just have to be a wizard about how to deal with that kind of stuff, which I am not. So we'll deal with it in a single-threaded manner here, and you just get to see the process, and I'll let you guys take it from there. Yes, sir? So the question was, does the process scale well to parallel computers using CUDA, right? And you actually brought up a good point. This process is optimized for CUDA core processing. My laptop, while it has a nice GPU, is not CUDA core, so it's going to do all CPU time. So CUDA core, it like doubles the processing speed of all of this stuff. So you hit on a good point. Look into that later. So, okay, well, we have all of the images here of this robot. We'll go ahead and select them all and bring them into VisualSFM. It takes a moment for everything to load up here. So we'll just take a sip, wait patiently, and let some magic happen. Bam. So I was talking about there being a few unwritten rules about how to make this process work well. So the key component is, since this is a purely optical process to acquire images, we need to have very even diffuse lighting. So even lighting all the way around to try and prevent as many shadows as possible will help the reconstruction algorithm create the shape. And you also have to take some considerations about like reflective surfaces or surfaces with any bit of specularity, like a half gloss, a semi-gloss metal surface. Like if it's reflecting any points of light, that distorts the result of the scan, but it doesn't ruin the scan. This is actually a really robust method of reconstruction. And another note to keep in mind is this works best on binary image types, monochrome image types. So it works just fine with color, but the more contrast you have between features, the more color differences you have, the better performing everything is. Now, in contrast, this process does not work very well with things that have very few features. Like if you look at like a bell that looks the same from all the surfaces, right? If it's what's known as a surface revolution, right? Like those types of features don't scan very well just because of the way the algorithms work. And conversely, things like circuit boards here with lots of, linear differentiating lines, those types of features pick up very, very well. So we'll go ahead and run this process here. And first thing we need to do is what's called compute missing matches. So this is going to run a process here. And let me pull up the log window so we can see what we're looking at. Show log window. So this is running through all my images, doing some feature detection. And now we need to do this sparse reconstruction. So here the software is running.
You're not doing any,
oh no.
motion analysis on the camera itself. So no gyro, no accelerometer. So it just figures out where the camera must have been for each image by trying to take them together.
You know what? Something happened here. Good thing I have more than one data set. So I'm sorry, what was that? I was a little distracted.
Maybe I'll let you finish.
No, there's no accelerometer on the camera. It just uses the image.
Correct.
You can take other people's images as long as they're of the same subject. There's a few sliding, not too many reflective surfaces, so it'll probably work in some cases.
Okay, so I've got another data set here that I know has worked. I don't know what went on here, but hey, demo gods, right? We'll try that process again. So the question that just happened a moment ago was, does the camera have an accelerometer to sort of place the image locations, right? And no, that it does not. However, this algorithm does look at EXIF data on your phone. So what you could do is you could mine photographs off the internet and take people's like Google image results of like the Arc de Triomphe or whatever landmark you can think of, and just mine other people's photographs, and the software works really, really well with that kind of stuff. I did a reconstruction of the Welcome to Las Vegas sign just as like a demonstration a few weeks ago, and it did a pretty darn good job just taking people's disparate images off the internet, and it created a reconstruction. Okay, so this is running a little bit better. And that's what I wanted to see. So here we have the software sort of placing each one of these photographs in the orientation which it was taken. This is running a piece of software called Bundler, which was not initially used for photogrammetry. This was more meant to like sort out your vacation photos and sort of like be able to recreate a panorama. That being said, the same exact technology is being used when you use a panorama function on your phone. You know how you have to like take one picture, move like 30 degrees, and then take another picture, so on and so forth. Same exact technology, same exact feature recognition. It happens when your camera automatically stitches all those frames together. So same exact kind of technology. This is what's called the sparse reconstruction. So you can sort of see each individual image in three-dimensional space where it would be projected. And you can also see what's called the sparse point cloud. You can sort of see what it's trying to reconstruct. So we still have a bit of processing to do here. And the majority of the processing happens in what's called the dense reconstruction. So this is going to use a little bit of processing power. First, it's going to run an algorithm to undistort each one of these images so it can accurately reconstruct the dense point cloud. This process is, like I was mentioning earlier, it's very dependent on optical properties. So like your lens properties are pretty important to getting your results. This does not work very well with fisheye lenses because that distorts straight edges. You want to try and have lenses that most closely represent the human eye, something between like a 35 to 50 millimeter lens. Telephoto lenses work really well just because there's almost zero distortion. What else am I thinking here real quick? The one key component is that you have enough overlapping segments so the reconstruction algorithm can determine, which photograph came subsequent to each next photograph, and that's why my first data set seemed to fall on its face. Yes, sir. Is the process friendly to cell phones, and how bad is the blurring? The images that we're looking at right now, we're taking on a cell phone, and it's a crappy $50 Huawei cell phone. So the photographs are not the best on this crappy phone, and the reconstruction is really good considering the circumstances. Now, with better photographs, you get better results. This is the overarching topic of what we're trying to cover here is you as the human are the noise filter in all of this. The computer can do a lot of stuff automatically on its own, but you sort of have to apply context and consider the noisiness of the image to what you're trying to scan. So, if you can get optimal lighting and eliminate as much of the background out of the image as possible, the reconstruction will be nearly perfect. But nominally, you don't always get that, right? Sometimes you have to scan things on site. You can't bring like a laser scanner out to it. There's no other way to image this thing. So you sort of have to work with what you've got. And photogrammetry gives you a lot of options. Like I was saying before, there's a couple limitations. It can't scan things like mirrors. It just has no idea how to, deal with, infinite depth like that at the moment. But it does give you a lot of leeway as to like the quality of your scan and the quality of the result. Now, one other thing to think about is how many megapixels does your camera have, right? Like, if I got a 50 megapixel camera and I'm trying to, take a 3D scan with, 1,000 photos, it could take potentially to like the heat death of the universe to process all of that. So there's sort of a non-intuitive factor with the quality of the image versus the quality of the result that with a higher megapixel rating camera does not necessarily produce a higher quality result, because with a higher megapixel camera you have smaller areas on the sensor that pick up each individual photon, and thus they're more susceptible to noise. So there seems to be a fine balance between megapixel rating and the quality of the result. 5 to 10 megapixels is all you need, because any more than that is just making the computer process way too much. And something else we're going to cover later on is once we've recreated the shape, sometimes you need to take it from a 1,000,000 polygon shape and reduce it to 100,000 polygons, 10,000 polygons, because what we're trying to accomplish here is make the resulting scan data like reasonably computable. Because if you're trying to do these, three-dimensional rotations of things with, millions of elements, I hope you have like 400 gigabytes of RAM on your computer, because, this is definitely pushing the resources of modern computing. So let's see what's going on here. This is going to be processing for another 10 minutes or so. Let's go through the scans here. So I was mentioning feature detection running through the SIFT algorithm, and that's running a specific kind of feature detection called difference of Gaussians. So what that does is it takes each individual photograph and makes subsequent blur layers. So if I pull up the photographs here, I can't do the blur here for you, but what the blur is trying to accomplish is it separates the differences between the features. Like wherever there's a sharp difference between the colors, between like the yellow and the black next to it, if you make blurs, it allows the computer to show like where the sharp edges are on each detail. So as it runs that algorithm through each individual frame, it can pick out, straight lines or the numbers or, the traces on the PCB. And that way it's able to detect, okay, there's a horizontal line here, vertical line here, hundreds of features per frame, and then make a comparative analysis between each frame and the features that they all contain. And through some kind of software magic, the algorithms here are able to discern like a three-dimensional shape on the resulting surface. Let's see here. So I was mentioning that we'll need a couple of pieces of software to do all of this processing. VisualSFM is enough to get us a point cloud and orient all of the pictures. And then we need to use another piece of software to sort of stitch that point cloud into something solid, something that's 3D printable, or something that is clean enough that you can take that information directly from Meshlab and import it into something like Unity or Unreal Engine. You know, you could make like a virtual garden of all the 3D scans you've ever done. And, you know, the data that we will end up with today, it will be directly transferable to any of those environments, or with a little bit of know-how, you can take these shapes and import them into engineering CAD software like SolidWorks or Fusion 360, just with a little bit of understanding with the file type nuances. So we talked about the applications already. So why is photogrammetry so cool? Unlike older styles of 3D scanning, we don't need to take like a very sensitive measurement with like a ruby tip and a physical machine and like measure all these points, right? That's one way to reconstruct a 3D shape, is just by touching it with a computer and taking measurements. You know, photogrammetry, like we can, you don't even have to touch the object. You know, 10 pictures, 40 pictures, you know, that takes you 5 minutes to do tops. You can use other people's images like I've been mentioning. Also, scaling is absolutely not a problem with photogrammetry, where other types of 3D scanning are very limited to a very small volume of space but at high resolution, or conversely, using a Kinect scanner, or Microsoft Kinect, it does a very like medium resolution of like medium to somewhat large shapes, but you quickly, you know, run out of size that you can scale down, or images that are too large it can't scan, where photogrammetry doesn't care, right? As long as you have enough processing power and you're patient enough to allow the processing to happen, right, the sky's the limit. You can image the world if you had a computer large enough. Talked about a few of the things up on the screen, that one of the main goals for this process is, unlike getting scans for 3D CAD, which is mostly important for dimensional accuracy, this process is uniquely applicable towards like gaming and rendering, where you don't worry so much about like the dimensional accuracy of things, but you're more looking for a visual appeal and the full color objects that, you know, you might be desiring for, you know, game development, or, you know, if you're working at the Smithsonian and you want to, you know, image some things and put them up online. That's really cool. So what does photogrammetry not do so well? I've mentioned before, it's really sensitive to lighting conditions. So with that in mind, I'll repeat again that diffuse, even lighting is how you get the best results out of this. There's also no inherent sense of scale with the photogrammetry results. I'll show you here later on, the overall world result is one unit, and then everything is based on a subdivision of that. So if you have a known dimension on the part, all you need to do is run a quick scaling operation, and then you get pretty darn close. And that's an easy number to fudge, right? Like computers don't mind, you know, scaling a three-dimensional table just a little bit. That's something else to consider, is all we're doing here is manipulating a three-dimensional matrix of, you know, several million elements. That's why we're using something like Meshlab to treat this in a mathematical sense, because 3D scanning, 3D printing, 3D CAD, all of these things are very dependent on having clean data. Now, the easiest way to visualize like the most basic file format for 3D scanning results, for an STL file or an OBJ file or a PLY file, the most basic form of any of those files is 3 dots in Cartesian space, right, like on an XYZ plane. So 3 dots in space with lines drawn between the dots, a face in between all those lines, and a surface normal, which tells the software which direction is pointing out for like lighting conditions. And you scale that over, you know, 1,000, 10,000, 100,000 triangles, and you can make a shape of almost, you know, any form with a reasonable enough resolution that it represents what you're trying to imagine. Now, that's distinct from 3D CAD files, which define dimensions based on line length and arc sizes, right? Like very, very accurate descriptions of, the dimensionality of parts, that's something you do not get using photogrammetry. Everything that we're dealing with here will result in straight lines and no dimensionality. So that is one of the hang-ups, but it's easily remedied by just knowing the software tools and what to look for. So some interesting things that I've come across learning about photogrammetry. I've been discovering a couple of things about computer science that weren't necessarily clear to me in the first place. And three-dimensional matching is kind of an interesting thing. So what we're going to be doing here at some point is we'll have a three-dimensional colorless shape. And remember all of those oriented photographs that we have? We're going to have to attach both of those in the software, and we have the colorless three-dimensional shape with the two-dimensional image that's aligned in each position. And we'll have to use the software to say, okay, project those colors that you see from each alignment and then reconstruct the color on the object. So the ability for me as a human to align a three-dimensional object with the two-dimensional image, that's pretty easy for me to do. I can say, okay, yeah, that's good enough, and that lines up. That is exquisitely difficult to get a computer to do because three-dimensional matching is a known NP-hard problem. It's without getting too buried into the computer theory about all this, there's some interesting questions that we can ask at this point, like, does P equal NP? Most people believe not, right? Like, there's some things that are just not efficiently computable. The Alan Turing came up with this thing known as the halting problem, right? How does a computer know when, the matches are, or when the shapes are matched up to the images closely enough? There's just some things that the computer can't figure out right now. It's not saying that it cannot be figured out, but that seems to be a pretty hard barrier at the moment. So it still requires a human like us to interpret the results a little bit for the computer. The computer's going to take care of the majority of the work, but you still have to go in and apply context, right? The computer has no idea what I'm trying to scan or what it's trying to image or what's important out of the image. And there's some really interesting things. If you've ever played with a Microsoft Kinect 3D scanner, it's old technology. It's using something that was developed in 2007. But the reason the technology is so good nowadays is because of advances in artificial intelligence, AI, trying to sort out the almost infinite amount of data that the sensor soaks up every millisecond and filter out, okay, this data is too far away, this data is too close, I'm just going to focus on what's in a specific range. Like I was saying, this kind of stuff is getting better and better every day, and there still seems to be some hard limitations on, what the computer can do and what the human still has to do. So luckily, if you're an artist and doing this kind of stuff, your job isn't going to be threatened anytime soon because, hey, AI isn't strong yet. But be wary, who knows what's going to happen later on down the road. A couple other things that we're going to have to consider that aren't necessarily clear right off the bat is when we're processing the point cloud, turning it into the STL where we have, the triangular faces drawn between, every little point. Now, it's easy for the computer to visualize just a big messy point cloud with a million points in space, but once you try and stitch all of those points together, sometimes there's little dangly points or edges just, floating out in space. And when you're talking about, a million edges on a three-dimensional scan, it's almost impossible as a human to go through and say, okay, there's, one point floating out in space that, would ruin the algorithm if I tried to, reconstruct the surface. So that's why we have to treat the results mathematically using something like Meshlab. Give me a second here. Oh, looks like we're finished, so we can actually just jump straight into Meshlab and process the results. Give me just a second. So, using the crappy camera phone data, can you see Dano's backpack and a coffee mug and a roll of tape on there? Can you see that? So this is we're about 50% in on this, right? You can see that there's some noisy artifacts, some of that dangling data I was telling you about. You can sort of see where back here on the right-hand side, there was like a toolbox that was imaged, and me as the human, I need to set some context to this data, right? I want to get rid of the outlying data and sort of like statistically optimize what I'm trying to reconstruct. Because the reconstruction algorithm I'm going to run is going to try and stitch together all the points globally. So if I remove the outlier data and focus on that core component that I was scanning on, we'll get the best results. So since this is just a point cloud at the moment, I need to delete all those extraneous points. So I'm not going to cover too many details about Meshlab at the moment, but I highly suggest that you check out YouTube because there are some wonderful Meshlab tutorials, and that's how I learned everything. I'm also firmly of the belief that Meshlab skills make your 3D printing or 3D imaging skills that much better and robust, because then you're able to not only discern the data a lot better, but you're also able to troubleshoot the data a lot better. So we're looking pretty clean. We got a couple of little outliers, and you'll never be able to remove all of the noise from this system. So this is a remarkably noise tolerant process, but nonetheless, your results are very dependent on how noisy the structure is. So like I was saying, I'm just removing a little bit of the noise here, right? Any of the little outlying data. And I believe that's good enough. So one thing about Meshlab, it's a little glitchy, right? It's free, it's open source, so you can't expect it to be perfect. So one very important lesson is save early and save often. It's also a destructive process. So there is no such thing as the back button. FYI, save at every step and you'll be much happier at the end, because I get a few glitches here and there every now and then. So just be aware. So I'm going to save this file out as just a point cloud at the moment. If I zoom in, you'll see that there's nothing connecting all those dots together. And there, like I was saying earlier, there's 3 overlapping file types, which all sort of work similarly when you're doing 3D point cloud reconstruction. Either the STL file format, which is the standard 3D printing file format, or you get POY and OBJ, which are related. So we'll save this out as a POY. That's just Meshlab's standard export file format. Now, this is the dense point cloud, right? We look in here and we can see all the little tiny points floating around, but nothing stitching everything together. We need to run a process to stitch everything together. And you find that in some of Meshlab's filters. The one I use 99% of the time is in the remeshing option here, and it's called Surface Reconstruction Poisson, right there. So magic numbers, the octree depth is 11, the solver divide is 10. Any less than that, you get really blocky coarse results. Any more than that, and you'll be processing for a couple of days. So those numbers are a little variable. You can bump them up or down 1 or 2, but watch the YouTube videos, play around with it on your own, and you'll sort of figure out which numbers work for you and what your processing time is like. So I hit apply, let the magic squirrels do their work here for about 90 seconds, and it's really, really cool what's going on here. You'll see the results. So this surface reconstruction algorithm is going to globally analyze all of the points on this file and stitch together to the best of its abilities like all of the resulting surfaces. I don't know, it makes me a little sad to think about how much of my life I've spent watching a status bar like slowly creeping across the screen, but I'm sure you guys have non-zero amounts of that too. So you can sort of see the reconstruction it made, right? There's a big surface that just kind of extends out into nothingness, but when you look at the core of everything, okay, yeah, there's actually quite a nice little surface, and even some of these little noisy points, like it completely negated, right? It's running this really complex statistical analysis to say, oh, these points are related, all of these kind of are in a similar plane, and any of the outliers it just kind of forgets about, right? Magic. I'm not a mathematician. I can't really explain how this works, but it just freaking works. So we have two meshes that are superimposed on one another, right? There's our initial point cloud, and there is the solid surface that we're left with. Now, there's a little bit of noise, right? Like it made this big extra artificial surface where I had nothing initially in the point cloud. And here's where we go back to what I was talking about, how we need to treat these, how we need to treat this process mathematically. Now, you'll notice that all the little points in here, you can't really see the edges. They're actually really close to one another, right? And you can see the edges out here, which are more artificial. All the edges are a little bit longer, right? So there's a specific filter in Meshlab that we can select the edges based on their length. Okay, so let me save this Poisson mesh. Remember what I said, save early and save often. Export this mesh as a Poisson. And Meshlab is very, very picky about which mesh you have active. The active mesh is the highlighted one. And there's also a mesh dialog box here, the layer dialog box, which gets you into that submenu. So we'll be dealing with this Poisson mesh, right? We got a bunch of little outliers and a bunch of extra little surfaces that we don't need. We want to delete all these extra, mostly artificial surfaces out here. So in the filter menu, we can select edges based on their length right here, edges longer than. And the default edge threshold is at about the 50th percentile mark. So without having to tweak that slider at all, I just hit apply, and it shows me which edges are the most artificial. And you could, change that slider around a little bit, and it will select, which edges are more or less artificial. But just by itself, it's pretty much okay. I'll run this process one more time because it'll be more refined here the next time through. But we'll just let it apply the selection to all of those artificial edges, and we'll go ahead and delete it. So what we're left with is a cleaner but not quite clean enough result, right? We got, a bunch of little dangly bits you can see over here, disconnected edges. We still got a couple of holes, but what we're trying to do is refine the math, refine the matrix table to triangles that are more reasonable to work with. The one very bad thing to have in a resulting mesh file is long, skinny triangles, because when you're applying like trigonometry to long, skinny angles, you sort of round off a lot of decimal places. You end up with a noisier, not as accurate result. So by refining the edges here, we're trying to get the highest quality edges with the most equilateral triangles, which you can apply more robust math to. So along that same line, we've got a lot of little like dangly bits here, tiny little isolated triangles or extra bits that would cause some errors to the further reconstruction that we need to do. There's more filters to get rid of all these little dangly bits. So on the filter menu, we go selection and small component selection. So right now, if I just hit apply, it will pick components that are less than 10% the size of the largest component on this entire mesh. So like we got a little dangly bit here. This is probably less than 10% the size of the largest component on the mesh. So if we hit apply, you'll see all the little bits get picked up, right? Even this bit over here, there's a couple of larger bits, but that's okay, right? We'll do this reconstruction one more time and we'll get a more refined result. So we'll go ahead and hit apply, hit delete. Oh, hold on, let me try that one more time. Third time's a charm, second time's a charm, something like that. So apply, delete. Okay, so we got some dangly edges, but we still also have some rough edges, right? We want to be able to refine some of those rough edges. You can see how they're sort of spiky here. The more rounded things are, the more continuous the curves are, the better the reconstructions will be. So there's one more filter we can run, a smoothing filter. So we got a Laplacian smooth. So see if you can see these spiky edges down here at the bottom. We hit apply. All the spikes go away, right? We're trying to eliminate the noise. Now, I was mentioning to you that sometimes there's some hidden data, right? There could possibly be a couple of points floating out in space or lines that aren't connected to triangles. We need to be able to sort all of those out and delete them, because the next few steps that we operate on need a perfectly clean mesh to be able to reapply the color to everything. So 2 more filters and then I'll stop boring you with that. So you'll also notice down here at the bottom of the Meshlab screen, there's a dialog that gives you how many vertices and how many faces are selected. And we'll see that here when we run a selection filter. So here we want to select non-manifold edges. If there's any lines that aren't connected to triangles, right? Non-manifoldness. So we hit apply. What did it select? It selected 13 vertices and 24 edges. It's a little hard to see right here on the bottom of my screen, but that's what you'll want to be looking for. There's 13 little hidden edges that are almost impossible to see. I'm not sure if you can even see that red dot right here in the middle of the screen, but there's one tiny little vertex that was just sort of left over because of that processing algorithm, right? Like 2 little dangly edges that the software neglected to get that will screw something up later on down the line. This is important, so otherwise I wouldn't be covering it, but just keep your mind tuned into that fact. So we hit apply, we got a few edges selected, bam, edges are gone. We'll do the same thing for non-manifold vertices. Same thing here, we want to hit apply. We want to make sure anything is selected. We got 39 vertices and no faces. And we'll go ahead and delete those vertices right there. No dangly vertices, no dangly edges. Save early and save often. So we'll export this mesh. Export the mesh as. Call it cloud clean. Actually, Poisson clean. This is not a cloud anymore. Okay, so if anybody missed that the first time, we'll run that process one more time. Since this data is much cleaner, if we run the surface reconstruction and cleaning process one more time, we'll end up with a really nice, solid, watertight surface. So we'll run that one more time real quickly. So what we want to do is remesh using a Poisson surface reconstruction with an octree depth of 11 and a solver divide of 10. If you hit the help menu, it explains a little bit about those processes. So we hit apply and wait for the magic squirrels. Everybody good so far? You lose anyone yet? Anybody cross-eyed? Yeah, we're good? How about a quick show of hands? Who's installed any of this software on their computer already? What you got? Okay, cool. Have you used it successfully yet? Oh, I was asking what piece of software the gentleman has over here, and he says he has VisualSFM on there, but has not used it yet?
I haven't used it yet.
Okay.
I'm trying to find a test data set to import.
I'll give you some when we're done. So remember how weird that reconstructed surface was last time? This is obviously much better because it's sort of seeing the continuous surfaces all the way around and producing a better result. You know, we're running the same steps through the process, but since the data has already been clean, we have a much easier result to deal with. So, okay, I don't even know if I want to delete that bottom surface. We'll just go ahead and work with what we've got here. I think this is good enough. So even though this extra surface down here at the bottom is artificial and recreated by the algorithm, the target surface that we're trying to scan and image is the silhouette of this backpack top here and the roll of tape and the Starbucks cup. And you can tell it's a little noisy, right? You can see a glitchy surface here. And that is completely due to the fact that I did this with a crappy, shaky camera phone. You know, if I spent some time and took some good, multi-megapixel images of that same scene, it would reconstruct better. But like I was saying before, you don't always have the optimal equipment. So we'll go ahead and save this out. Export mesh as, Bag solid. Okay. So that's all well and good. You know, we got this point cloud here, but what the hell happened to all that color I've been talking about, right? That's what we're really looking for, because the reconstructed surface here isn't that great, right? It's barely able to be discerned as a bag. Like maybe if I, change the lighting around, you can sort of see the differences in, the elevation of the surface. But what really will make this pop is applying the texture, the color back to this surface. And that's where this process really, really shines. So what we have to do is open a new project. There was a hidden data file that VisualSFM output with both the sparse point cloud. Remember the point cloud where it only had a few hundred points, but it also had all of the aligned images on that surface. And Meshlab can work directly with all of those aligned images to project the color onto the resulting surface. So very close to where we saved that last file is cameras.vt2.txt, right? Is that it? Oh, hold on. Bundle.rd.out, that's what I'm looking for. Now it's asking me for the list of cameras. Again, this is all online. So here's that sparse point cloud, kind of tough to see. Let's see if I can. Okay, so you can sort of see that point cloud here, right? And there's all that noisiness. But one extra dialogue that we have over here is the rasters, all the registered rasters, all the aligned images of that bag, right? So now we can sort of see how all of those images are aligned with that point cloud, right? That sparse point cloud. That's what VisualSFM went through and processed for us in the background. So the magic that we need to apply here, let's see, Control H, is we need to import that reconstructed high definition surface into this sparse point cloud. And those two are already going to be aligned since they were using the same data set. All you need to do is import the data set into this sparse point cloud. So we'll import a mesh from a few folders back into bag. Bag solid, right? That's the one that we just reconstructed. We have opened more than 100 meshes. Yay, we're the winner! So now, hopefully, you can see how that reconstructed surface lines up with that sparse point cloud, right? Our reconstructed surface has, 800,000 faces on it, right? Very, very high accuracy. It will be upwards of, 100 megabytes when we're done with all the coloring and texturing on this. So lots of data that we have here. If we hide that sparse point cloud, we still have the registered rasters, the aligned images, which show up aligned to that reconstructed surface, right? So the trick here, now that we have those files sort of aligned, we need to project the color onto that surface. And that's using a filter on texture called parameterization and texturing from registered rasters. So here we want to set the resulting texture file size. I like 4096, it's just a round number. I like to use UV stretching, and I turn off texture gutter, because what this is going to do is take the nominal, or the best colorization from each frame and apply the color. But by deleting this texture gutter, it's going to remove the seam in between each segment. So it works best by removing that texture gutter if you're trying to upload the result onto the internet using Sketchfab or whatever 3D imaging software you want. It produces the best resulting texture using these options. So 4096 texture size, I turn on UV stretching, and I turn off the texture gutter, which is set at a default of 4. So we'll go ahead and hit apply. And notice I just had to select the correct mesh because otherwise it wasn't going to do anything for me. So we'll go ahead and hit apply and let the magic swirls do their work, right? I wish I would have had some jokes prepared because this would be an awesome time. Like, just sitting here waiting, staring at my dumb face doesn't really help. But hey, so here we have the results using that data set that was not very clean to start with. And look at the amazing texture that it was able to pick up on this bag, right? Tiny little features and details it was able to make that reconstruction with to a very high degree of accuracy. And the best part about this is that it's also a renderable file, right? It's doing ray tracing and shadowing, and you can do ambient occlusion already, right? This is directly uploadable to things like Blender to do much higher end rendering, or Maya, or whatever, you know, your graphics preference is. There's also a lot of really neat rendering modes inside of Meshlab, so you can, you know, visualize that kind of stuff. So this is a really neat result, right? Like, my target was the bag. I didn't really care so much about that Starbucks cup, which is why you see a couple glitchy, non-filled surfaces, right? Like, the bag was my target, and in all the images that I took, I tried to center that bag as best as possible. So using a very low quality input, we're able to get a very high quality output based on, you know, just a couple of rules and knowing how the software works. Now, one other trick here. Okay, so we're talking about trying to isolate this kind of thing and make it a very friendly form to be able to 3D render, right? We're looking at, you know, 800,000 faces with full color. And while most modern computing hardware can render something like that, if this is just like a background detail in your like Fallout 4 mod, you probably don't need, you know, a background object to be 100 megabytes plus, right? Like, that's going to slow down your render time. You know, it's a little overkill. Like, we could image this very well with 1,000 polygons, but the texture is the most important part about this, right? Like, you can use photogrammetry to image the physical shape of something very, very accurately. But if all we're looking for is like a rough shape estimate, but a very high quality like a high quality color representation of the object, the process only requires a few more steps here that I'll show you. So I'll go ahead and clean up a little bit of this because, you know, we got all this extra noise out here that doesn't really, you know, apply to what's going on in this scan, where, you know, it's a little out of context here. So we'll go ahead and, you know, remove some of this. It's a little easier to see now, right? You know, we're running at like 20 frames a second, so, you know, even on some nice hardware here, it's still kind of pushing the limits. Give me just a moment and let me do some boring points and clicks. And the process we'll have to do, it's called quadric decimation and collapse. So we'll have to simplify these shapes by a certain threshold, but the object is to preserve the texture quality as much as possible, because that's, you know, what we're ultimately aiming for is, you know, a high quality color representation, a high quality visual representation of this object. So a little bit of cleaning. Okay, cool. You know, we don't have to get everything at the moment. This isn't, you know, trying to do this presentation for Carnegie Hall or anything. So right now we're looking at 800,000 faces, right? I actually didn't delete a whole lot out of there. So quadric edge collapse decimation with texture. That's the important one, because the with texture option preserves that texture the best. We got 800,000 faces right now, and in my research I've also realized that the human eye can hardly detect anything over 200,000 polygons. Like, you could sit here and hit that button a few times and slowly bring down the polygon count, and you won't see anything physically change unless it's under 200,000 polygons. But most of the time, you can get away with 2,000 polygons or 1,000 polygons. 10,000 seems like a nice mid-range. It mostly depends on how big the texture is that you're applying to the surface afterwards. So let's go ahead and reduce this down to 20,000 polygons right there. Bam. We'll hit apply and see if anything shifts on the screen. You might see a little bit move around, but it will be hardly detectable. Anybody see anything, right? Just a little tiny blip. You can still zoom in. You can still see the surfaces. And hey, guess what? These surfaces are actually showing up because they're looking at hard edges instead of soft edges, right? So if we're looking at soft edges, it's essentially the same, except now it's rendering at 60 frames a second because it's a much smaller image. And this, my friends, is the resulting file that you can export into, you know, a Unity environment, Maya 3D environment, right? This is a very, very cohesive file that you can take into many different pieces of software and, you know, deal with in a 3D way if you're trying to, you know, reverse engineer something or just for, you know, straight up visualization. That pretty much covers the majority of the process of photogrammetry, from acquisition to cleaning the mesh to the final rendering result. One last thing I wanted to show you is how to apply a scaling factor here. So if you ever have a known distance on your image, because reminder, photogrammetry is a naturally dimensionless method of reconstruction. If you ever have a known distance, like if we know that this buckle up here on the top, let me see, this buckle right here, if we know that distance is, you know, 40 millimeters or something, we can just do the comparison. Right now it's saying it's 0.27 units, and we just do a quick little conversion, apply a scaling factor, and then it's dimensionally accurate. So things are pretty much that simple. I think that pretty much covers the presentation I had for you guys, so I'm happy to answer any questions you guys have at the moment.
So if you, so we got this, and this is great, and this is the way we want it. If we did it again, and if the backpack flipped on the other side, is it a nightmare to like combine those two?
There's actually a really neat tool in Meshlab to stitch partial meshes together. And what you have to do is take the several partial images and you do a comparison on the screen. You have the two separate images and you have to say, okay, there's some common points between these images. And Meshlab does a really good job of like aligning all of that together. So I don't know if I have any data prepared that I can show you that right now, but ask me in 10 minutes and I can whip something up for you. So yes, there is some really neat tools in Meshlab that can allow you to take partial reconstructions and turn it into a solid full reconstruction. Does that answer your question?
Yeah.
Anybody else? Okay, smoke them if you got them. So thanks guys for listening, and yeah, that covers that. Whee! Yes, sir.
Sorry I missed the end, but I got some great notes. So.